All right, welcome back. Today's lecture, we're going to look at galvanic cells. You probably know them as batteries, and then we're going to look at how you write the notation for that, and then we may get into electrolytic cells today. So galvanic cells, the main thing to remember right off the bat, we're talking about a spontaneous reaction. Okay, spontaneous. So if it's a spontaneous reaction, um, oxidation reduction reaction or redox reaction, we call that a galvanic cell. So I like the apparatus that they have set up here. Um, it shows you one solution here, another solution here. Uh, you see this tube here, that's called a salt bridge, all right? So you need to know what that's called. That's a salt bridge. And that's where we get the work done, right? Like if I just mix the two solutions together, they would oxidize and reduce spontaneously, but I wouldn't get any electron flow there. So what we do is we put this salt bridge in here that allows electrons to flow freely from one side to the other side, but doesn't allow the solutions to flow from one side to the other side. So I don't know if you can, this one looks a little different, but generally we put, sometimes there's a little bit of cotton or some type of fritted tube, so it doesn't allow the solution to mix. And then we fill the salt bridge with some highly conductive solution like potassium chloride or something like that. So the reason why we want this separation is we want to get work done. We want electrons to be released by the zinc, and so we got a zinc metal plate here. And those electrons, because zinc is oxidized, they flow through the meter here. They come down to the other side and they attach themselves to the copper 2 positive ion solution. That's why it's that's why it's blue. It's the copper 2 positive ion. And so the two electrons attach here and they reduce the copper 2 positive ion to copper. So over time what you see is this solution is going to be less blue, right? Because as the copper 2 ion concentration decreases and it's deposited as copper solid on this copper metal plate here, you'll see that color dissipate. So that's a galvanic cell. It happens spontaneously. It has an electromotive force that drives the meter here. And we see how much force is there and what the potential, voltage potential is. That's what we're looking at. Let's see. Let me see. Did they say one other thing? No. Okay, let's go on. All right. So here you got to speak the language. I can't stress enough. There's a lot of terms in this chapter, and you have to know what they mean. So the zinc and copper bars that we saw, that the alligator clips, the clips that go to the voltmeter, were attached to, those are called electrodes. So zinc had its electrode, it was zinc. And copper had its electrode, it was copper. You can look back at it and see it looks like a copper penny, right? Although it's a long rectangle. So by definition, on a galvanic cell, the anode is where oxidation occurs. You must know that. On a galvanic cell, the anode is where the oxidation occurs. So what's going on there for the anode is the zinc solid is going to zinc 2 positive aqueous. And so it's being oxidized. So at the anode, oxidation occurs. The electrons flow through the meter, come out the other side, and the cathode and the galvanic cells where reduction occurs. So what's happening there is the copper 2 positive ion that was aqueous, the blue solution, gains those electrons and becomes copper solid. So we see the copper 2 ion being reduced. So each of these is a half reaction that we've been talking about. There's an oxidation half reaction that happens at the anode, and the reduction happens at the cathode, and these are called half cells. All right, and we need to keep those cells separate so we can get some work done out of them through the electron force there. All right, so here's the important part. It says to complete the electric circuit, we have to allow electrons to flow through the external wire through the voltmeter, out the other side, through the other electrode. And so we have to have a conducting medium through which the cations and anions can move through from one cell to the other cell, and that's called the salt bridge. All right. So the salt bridge allows the conducting medium which the cations and anions can move from one half cell to the other. Make sure you understand salt bridge. Again, why do we do that? We want those half cells separated so it's not just mixing and we don't get any work out of the electrons. We want the electrons to leave, go through that wire, come back on the other side so we can get some work out of the electrons. You guys see this all the time. When you turn the ignition key on your car, you're allowing the electrons to flow from one battery post, crank up the starter. We're using the electrons to crank the starter, and then the electrons come back to the other side of the battery post. Now, once the engine fires up, it starts reversing the process, right? It starts recharging your battery. But and the salt bridge, it's in there. It's usually some type of divider between them. But there has to be some way to separate the two reactions. All right, so this is the next thing that's really important, and I want you to be able to draw any galvanic cell with this notation. So what you have here is you always start with the anode. Then you have a line here. This is a boundary. And then you have the zinc ion solution, and you tell what the concentration of the zinc ion is in that solution. The double lines here represent the salt bridge. This is the salt bridge. That's telling people that this half cell is separated from this half cell. Then you have the solution in that half cell and its concentration. Then you have a boundary, and then you have what the electrode is made of. All right, so it says experimentally the difference in electrical potential between the anode and cathode is measured by the voltmeter, and that was the instrument we saw in volts, and it's called cell potential. You need to know that term. Cell potential, it's a subscript cell here with an E. So this is an important slide. I don't know if they spend enough time on it, but you're going to be able to calculate cell potential, and you're going to be able to have to draw a schematic of that, and that's what this does for us. Anode, solution in the half cell, salt bridge, solution in the cathode cell, and there's your cathode. Or the reduction cell, if you want to call it that. All right, standard reduction potentials. So somebody's calculated these all out for you. So here's how we determine standard reduction potential. So again, we've talked about this in chapter 5 in Gen Chem 1, which is about it was the introduction to thermodynamics, and we said we can't measure how much energy is in something directly. We can only measure changes in energy. And so if you go back to chapter 5, we said that the standard enthalpy of formation of any element in its standard state is referenced at 0 energy. Okay, so we have to have a reference point here. So we're doing the same thing here. We can't measure energy in these electrochemical cells by just the energy of one thing. We have to reference, we have to make one of the electrodes 0 energy so that all the energy is attributed to the other electrode. So this is what we do here. It's called a standard hydrogen electrode, SHE for short. And what it is 2 moles of hydrogen ion is reduced with 2 electrons and becomes hydrogen gas. So what you have here is you have a hydrochloric acid solution. This is a strong acid, so it's completely ionized into hydrogen ions and chloride ions. You have a current coming in here, and there's a piece of platinum wire here. And what's happening is the hydrogen ion comes up to here. It accepts the 2 electrons coming down the wire. It turns into hydrogen gas. You see the bubbles here. And that's my reference. All right. So the cell potential for this electrode is equal to 0 volts. So any change is going to be attributed by the other electrode that this electrode is attached to or referenced to. Okay, so again, we're going to have this. There's another half cell over here somewhere that this is. So we got the voltmeter here, and then it's coming over here. And there's another electrode here, another solution here. So any changes in electrical any voltage, we're going to assume it's to this because we've made our standard arbitrary standard of 0 for this standard hydrogen electrode, and it's very specific. It has to be 1 atmosphere hydrogen gas here, and it has to be 1 molar hydrogen ions here. All right. So make sure you know that this is this reference point for all of the voltage calculations we're going to be doing in this class and physics. All right, so here's a better picture of it. Okay, so here's what we have. You have a zinc solution here, just like we had originally. Here's my zinc electrode. It's a piece of zinc metal. There it is. Reduction is going to occur here. The zinc 2 positive is going, or the oxidation is going to occur here. Yes, at the anode. The zinc is going to lose 2 electrons and become zinc 2 positive. The electrons are going to flow through this wire here, up through the voltmeter, and then it go out the other side, and it registers a potential of voltage at 0.76. The electrons then go in here into my 1 molar hydrochloric acid solution, where 1 mole hydrogen gas at 1 atmosphere pressure here above it. And so, and then the electrons are able to flow freely through the salt bridge so that we have a complete circuit, because in order for something to conduct electricity, it has to have that complete circuit. And so we base all of this voltage on the zinc oxidation. All right, we assume that this contributes 0 voltage to the cell. So we do the same thing for the copper. So here we've put the standard hydrogen electrode on this side, and we have the copper solution on this side. So here's what's going to happen is the electrons come in here, and they attach themselves to the copper 2 positive, and then the copper 2 positive becomes copper because the copper 2 positives are reduced. So any reaction here, any voltage here, we reference to the copper. All right. So this is what's cool about this, is that once we got these referenced, they're referenced that way forever, right? So for that concentration and for copper, and that concentration of zinc solution and zinc. So now we have cell potentials for both zinc, the zinc reaction, half reaction or half cell, and we have the cell potential for the copper 2 positive ion half cell. And so here's what we got to do. So make sure you can write this structure and understand. Here's zinc, your anode. Here's your zinc ion solution. And then we have a salt bridge, and then we have the hydrogen ion solution. We have the hydrogen gas. That's another part of that standard hydrogen electrode. And then we have the metal anode there, the platinum. So with the zinc, it's being oxidized. Here we have this. The other electrode was where the reduction's taking place. The 2 hydrogen ions from the hydrochloric acid is gaining 2 electrons to become hydrogen gas. We got 2 electrons on the reactant side, 2 electrons on the product side. Those cancel each other out. We add these together, and that's the overall reaction between zinc solution and the standard hydrogen electrode. So here's the next thing to focus on. E-cell potential. Standard E-cell potential is always the standard cell potential for the cathode minus the standard cell potential for the anode. So here, the standard cell potential, we've already said this is the reference, that this is 0. And what we registered on the voltmeter was 0.76 volts. So that was the standard cell potential. So we can solve for this, and I mean, if you want to get rid of the negative there, which we should, we say that the standard cell potential for zinc is equal to negative 0.76. All right, so let's go back. This was a positive. This is 0. This is negative. I moved the negative over to the other side. And so the standard cell potential for the zinc 2 positive being the zinc being oxidized to zinc 2 positive is negative 0.76. Standard reduction potential. So what this is saying is that the opposite. So we know in that reaction, really what's going on is zinc is going to be oxidized to zinc 2 positive plus the loss of 2 electrons. But the reduction potential is the reverse. That's what that's what we want to. We want to remember how we had that activity series in Gen Chem 1. Well, here the standard reduction potential is negative 0.76. So it's just the opposite of what happened at the electrode for this case. But the zinc 2 positive gaining 2 electrons. This is a reduction because the electrons are on the reactant side to form zinc solid. That's called a reduction. And the standard reduction potential is 0.76. Now you're going again, well, that's not what happened, right? Yeah, you're right. This happened. This was a positive 0.76. And we can prove that if you go back to that last slide. It was a positive 0.76 for the cell potential. All right? So, but we're trying to solve for this reduction potential, the reduction. And so that's what we're getting, negative 0.76. All right, so let's look at this. Let's look at another cell. And so you may want to draw a picture. Like you may want to say, okay, I've got this cell here, half cell, and I have a magnesium electrode. All right, tells you that right there. There's your metal electrode. In here is a magnesium 2 positive solution. And they tell you that the concentration is 1.0 molar. All right, then you have another half cell over here. It has a cadmium electrode. How do you know? Because it says right there. Usually that's the way it works, right? Whatever this solution is that. We know that the solution in here is cadmium 2 positive, and that its concentration is also 1.0 molar. So those are connected to a voltmeter. So there's that. And then we have the salt bridge that allows electron transfer from one half cell to the other cell. Now, what's cool about this is all of these cells, they have been referenced to the standard hydrogen electrode. And so there's a table of these values, and you just look these up. So you look in the back of the book and you'll see that magnesium being reduced to magnesium, so they're always reduction, these are called standard reduction potentials, is a negative 2.37 volts. And the standard reduction potential of the cadmium 2 positive, gain 2 electrons, become cadmium metal, is negative 0.40 volts. So when you look at this, it says the galvanic cell, so it has to be spontaneous. That means one thing's going to lose electrons, and the other thing's going to gain. The magnesium is going to oxidize, and it's going to go this way, right? So that's going to make that a positive 2.73. That's a larger value, a positive 2.73. So then this must be, this is going to be reduced. So the cadmium will be reduced. The magnesium will be oxidized because oxidation occurs at the anode, reduction occurs at the cathode. So if I add these two numbers, or I want to calculate the overall cell potential, it's always cathode minus the anode, right? Always cathode minus the anode. And so we have the cathode negative 0.40 minus the negative 2.37. The overall voltage is 1.97. So we got a positive voltage here. This is a spontaneous reaction that has 1.97 volts of potential there. So again, what do we know? The magnesium is oxidized, and it's always cathode minus the anode, so minus a negative 2.37 gives me a positive 2.37. The reduction we already saw was negative 0.40. That's the cathode. So we plug that into this equation, which you need to know. The negative and negative make this a positive 2.37 and makes the overall voltage 1.97. All right? And you go, well, how do you know which one's going to be oxidized and which one's going to be reduced? Well, here's what you know. This is the most important part right here. If it's a galvanic cell, like a battery, it has to be spontaneous, and it's only spontaneous when the voltage is going to be a positive value. All right? So that's how we know for sure the magnesium is going to be oxidized and the cadmium is going to be reduced. Now, let me give you another reason why you know it's going to work this way. If you look on the periodic table, so here's my periodic table, right? And again, this is in Gen Chem. I don't know, again, you may want to refresh your memory. That activity series, you know the metals on this side versus the metals here. These want to lose electrons to become isoelectronic with the noble gases over here. So magnesium being over here is more likely to lose its 2 electrons and become isoelectronic with, let's see, let me think about it for a minute. Helium or neon. Neon, yeah, neon, then cadmium is going to lose its 2 electrons. And it's still not isoelectronic with the noble gas. So in this situation, you know this is what's going to be oxidized and this is what's going to be reduced. Magnesium is going to be oxidized, which means the cadmium 2 positive ion has to be reduced. All right, it says predict what redox reaction will take place, if any, when molecular bromine is added to 1 molar sodium iodide. All right. So what we're going to look at here is the sodium is already isoelectronic. This sodium here is already isoelectronic, right, with neon. So there's no reaction. This sodium's a spectator ion. So what we're really going to focus on is the bromine and the iodide. So we're going to have bromine. We're going to react that with iodide. And that's going to, if something's going to happen, we're going to form 2 moles of the iodide ion. And I should make it 2 here. Oops. 2 moles of, no, I should do this. Iodine, 2 moles of iodine becomes iodine. And we get 2 moles of the bromide ion. All right. So bromine is each bromine is going to gain an electron. Each iodide is going to lose that electron, become iodine. And so that's what we're going to look at. That's what we're going to investigate. All right. So here's bromine's reduction potential. You look that up in a table. It's 1.07. It's a positive value. That reaction looks like it wants to happen, right? Positive. Here's iodine. It has a reduction potential of 0.53, okay, which is less than the bromine's reduction potential. So if it's going to be a galvanic cell, this reaction is going to happen this way. It's going to force this reaction to happen that way. Is that what we have up here? Bromine is oxidized, or being reduced, and iodine is the iodide ion is oxidized, which is this reaction, right? It's reduction in the forward direction, it's oxidation in the reverse direction. So that looks like that's going to happen. It says predict what redox reaction will take place, if any, when molecular bromine is added to this solution. So let's see what the next slide looks like. So yeah, we write this. We write the reaction just like I had. Bromine, 2 moles of iodine forms 2 moles of bromide ion, and the iodine ion. So this reaction will occur, it says, because the reduction potential of this is greater than the iodine, the bromine will be reduced and the iodide ion will be oxidized, and this reaction will occur. Do they show us a nice calculation for that? Or I've already done it, but nope, didn't do it. All right, so I've already done that. Here's what I said. This is larger. This reaction will go in the forward direction. So the bromine will be reduced. And that forces this reaction to go in reverse because then the iodide ion has to be oxidized. But because this number is smaller than this number, yes, the reaction will happen. So what we would have here is the E cell potential equals the E cell of the cathode minus the E cell, the standard E cell of the anode. So the cathode is where reduction takes place. So that would be 1.07. It's being reduced. And the anode is where oxidation takes place. So that would be minus 0.53 volts. If we add those together, we're going to get a positive value here. And I should be able to do that, right? 0.5. Well, it's not that. But you can calculate that out. Should I be able to do that? Yeah, 0.477 or something like that. So we can calculate that out. So it comes out to be 0.4. Is that right? Or 0.5. 0.477. All right. Okay. So that's what we're doing here. So then they want you to see what happens here. Again, sodium's a spectator ion. What we want to know is which one's going to work here. Can the bromine go this direction and force the chloride ion this direction? Would that be spontaneous? Well, when you go the opposite direction, that's going to make that negative, right? And this number is larger than this number, so that reaction is not going to happen. So again, let's see what they say. So they draw the reaction. They say bromine being reduced, chloride ion being oxidized. But chlorine is more readily reduced than bromine, so bromine, and there's a typo there, bromine is not reduced by the chloride ion. So that reaction does not occur. And again, you can prove it to yourself. Calculate the cell potential, and that's going to be the standard. Look at the cathode minus the standard cell potential of the anode. And you're going to find out you get a negative value there, and that's not spontaneous. That's not spontaneous. If you want a spontaneous reaction, the cell potential has to be a positive value. All right, so we're at 28 minutes. Let's continue on. So that's the whole thing why we do this, is to determine the spontaneity of the redox reaction under standard state conditions. Because galvanic cells are like batteries, they're spontaneous, we want to determine whether that reaction is going to happen or not. Am I going to get a positive cell potential? And if I get a positive cell potential, then I'm going to assume the reaction is spontaneous. Now, there's some things you're going to have to know here, and you're going to have to memorize these. This is something you're going to have to memorize. 1 Faraday is equal to 96,500 coulombs per mole of electrons. 1 joule is 1 coulomb times 1 volt. And so here's the conversion of coulombs into joules per volt per mole of electrons. And then the maximum work here is done by electrical work, and that is negative the number of moles times Faradays times the cell potential. All right. So the total charge is the number of electrons that are and Faradays there, which is coulomb per number of moles of electrons, and then Faradays are coulombs per mole of electrons. So you got to memorize this stuff, and you probably will have it memorized by the time you get done with the homework, because you're going to be using these as like conversion factors. the main one, I think, still, I wish they wouldn't break it out, is this or that equal to this down here. All right. So here is where we tie in what we learned in chapter 18 with chapter 19. And I just find people who have not mastered the Gibbs free energy in chapter 18, it all falls apart here, and they just really struggle with this chapter. It's similar to in Gen Chem 1, you had to know Lewis structures in order to do molecular geometries. And you had to know molecular geometries in order to talk about intermolecular forces. So the same thing here. If you don't know delta G, you have no shot at this. So delta G is the ability to do work. That's what Gibbs free energy is all about. And the ability to do work is that spontaneity, right? And so delta G is equal to work max. And so we substitute in for work max as delta G equals negative the number of moles of electron times Faraday's times the cell potential. Now, the relationship between this one and this is under standard conditions, and we have to have standard cell potentials. And you go, why do we want to have that? Well, these cell potentials can be looked up in a table. They've been done for you. That's why we like the standard. And then we saw in the previous chapter that standard Gibbs free energy is equal to negative negative RT-ln of K, the equilibrium constant. So we could substitute in for delta G naught this, and we set that equal to delta G naught equals NFE, the cell potential. And so we see the relationship between equilibrium and cell potential. Now, what I think is really cool about this, like when your battery's dead, let's say you go out to your car, you turn the ignition, you hear it, or you might hear a click. Doesn't mean that the battery's chemistry is done. It doesn't mean that there's no potential energy left in your battery. It just means it's come to equilibrium, or come to equilibrium with the force required to crank that starter. So I think that's important to know, is that delta G equals 0 is equilibrium, and so we're looking at that in this situation here. So we're going to solve for the standard cell potential. So again, what are we doing here? We're taking the relationship that we have here at the bottom, and we're going to solve for standard cell potential here. So we get this equation. R is a constant, temperature 298 Kelvin, N is number of moles of electrons, and there's Faraday's 96,500 joules per volt mole. All right, so then we get this equation, because all they've done here is these two constants. We can divide that, and we get this number divided by the number of moles of electrons, ln of K. And then we want to solve for the cell potential. If we want to make it base 10 logarithm, then this number becomes 0.0592. So you'll probably need to know this equation here or this one here. Both of them work, okay? Both of them work. It's whichever one you want to use there. So to determine the standard potential of the cell based on the number of moles of electrons, we can do that in the equilibrium constant. So you can see what's going to happen here. If you got a large equilibrium constant, that's a positive value, right? And that's going to give you a positive value here. But if you've got a K that's less than 1, this term is going to become negative, and you're going to have a negative cell potential, and it's not going to be spontaneous. So I want you to think like that. Kind of think about, plug some numbers in here and think about how that affects this number here. All right, so let's look at this problem. This is a good problem. It says calculate the standard free energy change for the following reaction at 25 degrees Celsius. So we can see from this reaction calcium ions being reduced and silver is being oxidized. And they tell us the concentrations. Okay, so at the cathode of a galvanic cell, that's where reduction takes place. the calcium is gaining electrons. How many is it gaining? Well, because there's 3 calciums, each one's losing 2 electrons. It's gaining 6 electrons to become calcium solid. That's a reduction. So we can't have reduction without oxidation. So here we have 2 moles of silver becoming 2 moles of silver 3 positive ions, and we have the loss of 6 electrons. So we go to the table and we find out that the standard reduction potential for calcium is negative 2.87, and standard reduction potential for silver is 1.50 volts. So from our previous slides, we know that the standard cell potential is always cathode minus anode. So we put in the negative 2.87 for the cathode, where the reduction of the calcium 2 positive ion to calcium is happening, minus the anode, where the oxidation of the gold is going to gold 3 positive. And we get a cell potential of negative 4.37 volts. And you go, that doesn't sound good. That's it's not a positive value, it's a negative value. So this reaction doesn't seem like it's going to be spontaneous. Because we want a positive cell potential to drive the electrons through the wire, right? So let's go on and see what happens. The number of electrons exchanged in this reaction was 6. We have 96,500 joules per volt mole per mole of electrons, and we have a cell potential energy of negative 4.37 volts. We know we set this up right. These cancel out. That's moles of electrons. That gives us joules per, well, those are electrons. Yeah, I should say that, not moles of electrons, just electrons. And that gives us joules per mole. And if we convert that to kilojoules, we get 2.53 times 10 to the third kilojoules per mole. That's a positive value for delta G, and you go, if it's positive for delta G, it's non-spontaneous, right? So that's where we tie into chapter 18. So not a good battery, not a good battery there. It's not going to generate energy for us spontaneously. Now the reverse, but you got to think that way too. The reverse reaction will happen. The reverse reaction will happen. All right, let's look at another example. So here we have tin going to tin 2 positive. So there's oxidation here. Then the reduction of the copper 2 positive ion to copper 1 positive. So we're not going back to the metal here. We're going to a copper positive 1. So we balance this. We have to have 2 copper here. We've got to have 2 copper here. Gain of 2 electrons. That's the reduction. And the oxidation is the tin going to tin 2 positive and the loss of 2 electrons. We look up the standard reduction potentials for both of these in the back of the book. And then we say the standard cell potential is equal to the cathode minus the anode. So we plug in the values. Here's the reduction for the copper. This is at the anode, we're looking at the oxidation of the tin to tin 2 positive, and its reduction potential is negative 0.14. So we have that. And so if we add these two together, we get a positive 0.29 volts. That's not bad. It's a positive value. It's not a negative value. And we plug that into, here they're solving for the equilibrium constant. When we plug that in, solving for the equilibrium constant, we get an equilibrium of 6.6 times 10 to the ninth. And we know an equilibrium constant of 6 times 10 to the ninth is a reaction that goes far to the right. Far to the right. And so this reaction probably, I mean, we can plug it into the other equation and we'll find out that it's spontaneous. Do they do that for us? No. I mean, I would do that. Let's go back. I mean, if you plug that big number in here, 1 times 10 to the ninth or whatever, these are all positive values, right? And that's going to make the delta G negative, and that's the spontaneous reaction. So that's a good problem. Both of these are good problems. I just like, you always want the battery to work, right? You always want the battery to work. It doesn't always work. So you say, are these both batteries? They are, because they are set up as galvanic cells. It's just that the one's not going to do anything spontaneously. So I don't know if you want to consider that a battery, but it's set up like a battery, but it's not spontaneous. Now, so I would say, I wouldn't call the other one a battery. I guess I'd call that an electrolytic cell, because I'm going to have to force it to go the other direction for it to happen. This reaction, though, with the tin, I don't. All right. Let's go on and talk about the Nernst equation, and then we'll stop after this section here. So the Nernst equation is what you're going to use over and over again in this section. And that is, you start off with the general balanced chemical equation. We know from chapter 18, delta G is equal to delta G naught plus RT ln of Q, the reaction quotient, which we've learned from chapter 15? 14? So then for delta G, we're going to plug in this value. Delta G naught, we're going to plug in this value. So we get this equation. And then we're going to solve for the cell potential. Not the standard cell potential, just the cell potential. So we get the cell potential is equal to the standard cell potential, which we can calculate using the data from the table, minus RT NF ln of Q. All right? So stop here. See if you can manipulate this to this. If you can, you're in good shape. You understand the math of it. And it's worth doing. All right. So then R is a constant. And this Faraday's is a constant. And so if we're dealing with the ln of Q, this comes out to be 0.0257 volts over N. If we're dealing with the log of Q, it's 0.0592 volts over N. So it's the standard cell potential minus this. And that makes sense, right? Because this is contributing the reaction quotient related to K. We know if the reaction quotient is less than K, the reaction is going to go in the forward direction. If reaction quotient is greater than K, the reverse reaction wants to happen. So that's what this factor is doing for us. So these are called the Nernst equations, whether you base it on a natural log or a base 10 log. And you must know this equation, the Nernst equation. And you're going to plug in values for this and solve for either the cell potential, or the number of electrons, or the Q. Okay, so let's look at a reaction here. It says predict whether the following reaction will occur spontaneously as written at 298 Kelvin. So we've got to have a temperature, right? Because we saw that with the Nernst equation. So we have cobalt being oxidized to cobalt 2 positive. We have iron 2 positive ions being reduced to iron. And they tell us, we assume the concentrations of these are in moles per liter, 0.15 molar for the cobalt ion and 0.68 molar for the iron ion. So, first thing we know is that the iron is being reduced. The cobalt is being oxidized. Again, oxidation occurs at the anode. Reduction occurs at the cathode. And that's what defines the galvanic cell, right? Anode is oxidation, cathode is reduction. So here's our cell potentials. So we look at these up and we say the cathode is where reduction takes place. And then at the anode, even though this is the reduction potential, it's taking care of the anode. We say minus the reduction potential. Again, we look these up in the table. These are both standard reduction potentials. And the negative is taken care of here with this subtraction for the anode. We get a negative 0.16 volts. You go, oh, that's not too good. It's not the best. I mean, it's small, but this is the standard cell potential. This isn't going to tell us what the cell potential is. And then Q is always, products over reactants. And so we know what those concentrations are. And so Q is 0.22. All right. So again, all this stuff that we've learned this semester coming together for direct applications into electrochemistry. All right, so let's plug it all in here. We calculated the standard cell potential from the table. We know that 2 electrons are what's being exchanged here. And the Q is 0.22, and we take the log of it. And we come out with the value of negative 0.14 volts. So this didn't help enough to overcome this negative value here. And the reaction is not spontaneous. So, even though it's a galvanic cell, not spontaneous, not working for us. All right? Not a good cell, right? Now, can it be changed? That's the question. Can there something I could do here to make it spontaneous? Well, this part's fixed, right? This can't be changed. But what about this? Can this be changed? All right, so spontaneity of redox reactions under conditions other than standard state. Concentration cells. Because electropotential depends on ion concentrations, it is possible to construct a galvanic cell from 2 half cells composed of the same material but different ion concentrations. Maybe you've seen this before. You ever seen where they take a pickle or a potato, they plug in one electrode here and one electrode here, and it runs a clock here? And it could be that the concentrations are different here and here, and that can cause a potential energy difference, enough potential energy difference to actually run a little LED clock. So that's what this is called. Concentration cells. The same material, but different ion concentrations. And we know this can happen because we just saw where Q is important here. Whoops. Okay, so let's move on to that. So notice this is called a concentration cell. And you're going, how do I know it's a concentration scale? Well, look at this. Zinc electrode, zinc electrode. Zinc anode, zinc cathode. Zinc solutions, different concentrations though. And there's my salt bridge. Look at the picture. Same thing here. Okay. So what's going on here is because there's a concentration gradient, we can get a cell potential difference here. So overall, we know what's going on. One place the concentration's lower, that's the zinc's being oxidized. Concentration of the ion's higher, it's being reduced, and we can calculate what that difference is going to be. So the cell potential is 0, right? There's no cell potential here. They both have the same, it'd be cathode minus anode, it's going to equal 0. But the Q part, so we have differences here, and it's 0.1 molar for the product over 1 molar for the reactant, and we get a slight positive cell potential, which says this reaction is spontaneous, and that's how that a cucumber, I've seen it as a pickle, and I've seen it as a potato, can power an LED clock. All right, I'm running out of time. I'm going to stop here. I will pick up on this. There's not really that much left. I think it's just this one example to finish up 9.5, but I am going to stop here.